All right, this is a note reading of the Unit 6, which is atomic structure. We'll be covering that in the 12th week from about November the 12th to November the 15th. And in your textbook, this is really a summary of Chapter 6, as well as some of the NIMSY notes as well. So what you're going to be seeing here is, if you've had physics, it's going to look very familiar to you, and if you haven't, that's okay. Hopefully this will give you everything you need to know. So we're talking about waves, and this is a subject that almost belongs more in physics than in chemistry, but it is treated as an AP chemistry topic, and so we're going to go ahead and deal with it. So electromagnetic waves. So understanding electromagnetic waves and light is necessary to understanding how energy is transferred into and out of an atom. Now, when we just recently talked about thermochemistry, we talked about energy as being heat. And almost always when we talk about chemistry and chemical reactions, it is heat energy. That's the kind of energy we're dealing with. However, this is talking about energy in and out of an atom, just one specific atom. And so in this case, we're talking about what are called electromagnetic waves. Visible light is one kind of electromagnetic wave. All the energy we receive from the sun is in the form of electromagnetic waves. A transverse wave, which is the type that you see here, moves in a roller coaster fashion. The top of the wave is called a crest, and the bottom is called a trough. The distance from a point on one wave to the identical point on the next wave over is called a wavelength. So up here you see from the crest here to the crest there would be a wavelength. But just as easily we could have said from this point right here to the identical point over here would have been one wavelength as well, and that would be exactly the same distance as this is right here. It's usually measured from crest to crest because that's just the easiest to visualize. A cycle is one movement of a wave, for example, from one crest to the next. A wavelength is the straight line distance between crests. A cycle is one complete down and up movement between crests. Waves have properties of both continuous waves and particles. I should have said, yeah, that's true. Electromagnetic waves have both properties. We're going to talk about that. So in other words, what's the difference between a wavelength and a cycle? A wavelength is a distance. It's measured in meters or micrometers or nanometers or something. And it's the distance, say, from straight line distance from here to here. Whereas one cycle is simply one complete motion of the wave from here to here. So they're not the same thing, even though they start and they begin and end at the same place. In this case, the wavelength is actually a distance, and a cycle is just a number. It's how many times did it go up and down like that. All right. Wave properties of light. So this is, if you took physics, this is what you learned about light and electromagnetic waves, that they are waves. So frequency, get this adjusted, frequency, and that's uses the symbol nu, pronounced nu. It looks like a V. It looks like what you might have seen in physics as velocity, but it's not. It's actually a kind of a V-type character. It's a Greek letter, and it's pronounced nu. Is how many cycles pass a point each second. The units of measure for frequency are cycles per second. Oftentimes you'll see that written as 1 over S. It's just simply over seconds because, as I say, cycles is just a number. So it's number of cycles for every second, or S to the minus 1, which is another way of saying 1 over S. The most common measure of frequency of cycles per second of saying it's the more common way of saying it is hertz, and it's just Hz. So hertz means cycles per second. Period is the time it takes for one cycle to pass a point. The period, which has the abbreviation capital T, is measured in seconds. In figure 3 below, SpongeBob is standing above crest 0 when his watch reads 0 seconds. So let me flip over to that real quickly and show you what we're talking about here. So a cycle is, here are the definitions. A cycle is a movement through a wave. So SpongeBob slides down from crest 0 and back up to crest 1. He goes like that. A frequency is how many cycles pass a point each second. or past SpongeBob, assuming he stays there at crest 0. He doesn't slide down. He stays there, and he watches this wave. You see the wave direction is to the right. If he just stands there and watches the wave go by, it's how many of these cycles will go past him in 1 second, and that's called the frequency. And the period is the amount of time it takes, it should be 1 cycle to pass SpongeBob. So let's say, as in an example here, at 0 seconds, crest 0 is below SpongeBob. So that's right here, that's 0 seconds, and he's standing right above crest number 0. 1 second later, crest 4 is below SpongeBob. So here's 1 second later, and this crest has moved over to be below him. So this is kind of like a before and after picture. So this crest 4, it's the same wave, but 1 second later, it's now below him. This means that 4 cycles passed in 1 second, which is a frequency of 4 hertz. So the wave just passed and went 1, 2, 3, 4, except the wave is moving to the right and the 4 is down there. The period is 1/4 because this is the time it takes 1 cycle. So in other words, if 4 cycles pass in 1 second, then each cycle takes 1/4 of a second, another 1/4 is 1/2 a second, another 1/4 is 3/4 of a second, and another 1/4 is 1 full second. So if you notice the relationship of those numbers, 4 cycles is the frequency and 1/4 second is the period, that the frequency is the reciprocal of the period and vice versa the other way around. The period would be the reciprocal of the frequency. All right. Okay, so let's go back to the first page again, continue reading. So it says, SpongeBob is standing at crest 0 when his watch reads 0 seconds. 1 second later, the wave has moved to the right and he is standing above crest 4. This means that 4 cycles have passed in 1 second for a frequency of 4 hertz. It also means that each cycle took 1/4 of a second, which is the period of the wave. A transverse wave describes the shape of a wave as an up and down wave, such as you can create with a spring or a rope. Electromagnetic waves have an electric part and a magnetic part that travel together at right angles to each other. So this is actually an electromagnetic wave because it does include components of both. And if the electric wave is going in an up and down on an up and down axis or an up and down plane, that would be, then the magnetic part, the electric part's up and down, the magnetic part would be perpendicular to that, but traveling in sync with it. So they have to be traveling together. Okay, so energy from atoms comes in the form of electromagnetic waves. Light is one of many types of electromagnetic waves. All of the energy Earth receives from the sun is in the form of electromagnetic waves. Figure 4 on page 13 shows, now I haven't given that to you by the way, I'm going to give that to you tomorrow. Figure 4 on page 13 shows the electromagnetic spectrum, which displays all of the kinds of electromagnetic waves. All electromagnetic waves travel at the speed of light, which is 3 times 10 to the 8th meters per second. Some of your worksheets will have a more precise number, 2.99, but generally it's oftentimes it's said 3. The speed of light is represented by a lowercase c. The speed of an electromagnetic wave is given by the electromagnetic wave speed equation, which is the speed of light. So this number is always 3 times 10 to the 8th, equals the wavelength times the frequency. And as I mentioned in class, in your physics classes, you probably used the letter F for frequency. Now you're using this V-like character called nu, so don't get it confused. It's not velocity. It's not wave speed. It is frequency. Now, since both of these multiplied together have to always come out to be 3 times 10 to the 8th, you can infer from that that if wavelength gets bigger or longer, frequency will get smaller or shorter. And if wavelength gets much shorter, then frequency will get higher. You will have a higher frequency. So these two are inversely related, and they always have to multiply to be 3 times 10 to the 8th. That's only for electromagnetic waves, but that's the only kind of wave that we're going to be talking about. Okay, so here's a simple example problem. You're going to be dealing with some equations that look a little bit intimidating at first, but a lot of them are just plug and chug problems. You plug in the numbers, you come up with an answer. So here's an example. Wavelength times frequency must always equal 3 times 10 to the 8th. As one of these values gets larger, the other gets smaller. So example, what is the wavelength of an X-ray with a frequency of 1.5 times 10 to the 17th? And that should be hertz. Should always have units of measure there. I'll add that in. Which is cycles per second, or 1 over seconds. So we have our equation right there, and we're solving for wavelength. It's asking us for wavelength right there. So wavelength, if you just divide both sides by nu, and you'll get wavelength equals the speed of light over nu. So it's 3 times 10 to the 8 meters per second over 1.5 times 10 to the 17th seconds inverted. So if you can cancel the denominators of both of those, and you end up with just meters, and that is a unit of measure of distance. And that's going to give you 2 times 10 to the minus 9th meters, or 2 nanometers. Nanometers is a unit you should get used to hearing or seeing, because when we deal with light waves, many light waves are on the order of a nanometer, and so it's a unit of measure you're gonna hear a lot. So I'll just write it right here. 1 nanometer equals 10 to the minus 9th. It's 1/1 billionth of a meter. Okay, all right. Now we get into the thing that you may not have learned in physics class if you took regular physics. Maybe in advanced you did, or AP you definitely get into this. Or maybe not so much, because this has really become a chemistry, an AP Chem topic. Okay, so particle nature of light. Light also has the characteristic of an object, and these objects are called quanta. Quanta of light specifically are called photons. It's basically a discrete packet of light. It's not a big, long, continuous transverse wave like you're used to seeing or like you learned about in physics class. So a photon has a definite amount of energy based on the frequency and the wavelength of the light. Physicist Max Planck developed an equation for the amount of energy in a photon. The energy has the unit of measure of joules, which is what we always measure. It's what we measured heat energy, and that's the beauty of energy. It can be transferred in all these different forms. So the Planck-Einstein equation is E equals H, which is Planck's constant, and this is a number you'll probably have memorized in the next few days because you're going to use it so many times, times the wave frequency. By the way, I would add a little subscript here that it's the energy of a single photon. So this is E. I'm just adding a subscript underneath E. So it's the energy of a photon. All right, equals Planck's constant times the frequency. And just remember units of measure, that Planck's constant is in joule seconds, and frequency is in 1 over seconds. So if you cancel the seconds, you end up with a unit of joules, and that's what energy is measured in. It's measured in joules. Important, energy of a wave and its associated photon is a function only of the wave frequency, not the amplitude. And that's an interesting kind of counterintuitive point that we'll talk about in class. It's not how tall the wave is, how high it is. It's how fast its frequency is, or how high its frequency is, that determines its energy. Okay, so let's keep going. Let's do another simple plug and chug example here. So find the energy of a photon of red light with a frequency of 5 times 10 to the 14th hertz. Again, if you want to change hertz to 1 over second so you can cancel the units, you can do that. But it's not really necessary. You know that the energy, that E is going to be in joules, and you can just leave it like that. So the energy of a photon equals HV. There's Planck's constant. There is the frequency it gave you. You just plug in the numbers, and you get 3 times 10 to the minus 19th joules of energy in 1 photon of red light. And that's any kind of red light. Wherever you see red light, it's going to have a photon of it is going to have exactly that amount of energy. It doesn't matter whether it's on somebody's shirt or whether it's a light or what it is, it's going to have that much energy. Okay. The last equation relates wavelength to energy. Example, what is the energy of a, well, let me read the equation first. The electromagnetic wave speed equation and Planck's equation can be combined. So if you take C equals lambda nu, and you solve that for nu, you have nu equals C over lambda. Okay, and then you can go ahead and plug in nu right there. So it's going to be h times c over lambda, and so you end up with that. It's just combining the light speed equation and the Planck-Einstein equation together. So it basically, what does this do that the other one didn't? Well, it relates, instead of relating frequency to energy, it relates wavelength to energy. Again, these are both constants up here. Planck's constant doesn't change, and the speed of light doesn't change. So it relates the wavelength of the light rather than the frequency to the energy of one photon. So here's another plug-and-chug problem. What is the energy of a photon of blue light with a wavelength of 400 nanometers? We get used to seeing the numbers and wavelengths expressed like this. So what you need to do is convert that into a scientific notation number. So here's Planck's constant, here's the speed of light, and 400 nanometers is 400 times 10 to the minus 9th. And you may say, well, isn't scientific notation supposed to have a number between 1 and 10? We talked about that. And the answer is, it's not. When you do speed. When you do light speeds, they generally want to have it standardized around nanometers, 10 to the minus 9th. And that's usually in hundreds of nanometers when we talk about light waves. Therefore, with light waves, you'll usually see the coefficient be a number in the hundreds like that. Okay, it's no big deal, but just get used to seeing that. And what you'll end up with is 5 times 10 to the minus 19th joules. So you'll notice something. Compare blue light to red light up here. Blue light has about 40%, I should say about 60% or 66% more energy than does red light. It's a higher frequency, and it has more energy than red light does. Even if the red light is brighter, the blue light has more energy. That's kind of a counterintuitive concept, and we'll talk about that more in class. Okay, so matter can emit, give off, or absorb energy in whole number multiples of Planck's constant times frequency. So, for example, it could be 2 HV, 3 HV, 4 HV. So, in other words, energy can't be just any number you want it to be. It's got to be some whole number multiple of the frequency times Planck's constant. The idea that energy is released only in specific energy levels called quanta was observed in 3 ways. One is that this is the way that Planck did it. It was black-body radiation. He saw that the heat from the stove produced a specific color of red. That's one way. The photoelectric effect, that's what Einstein won the Nobel Prize for, is that only certain energies caused electrons to be released from a metal atom. And finally, by excited gases. The light produced from an excited gas such as neon and argon. So you hear of neon lights. They're really not just neon. They can be other noble gases, but they can be used to produce light. And they produce very specific quantas of energy. Very specific quantas of energy. So the quantized energy levels in atoms are called orbitals or shells. You've learned that a long time ago in this class. Electrons can only be at one of these energy levels. These are similar to steps on a ladder. You cannot stand in between steps. You must either be on the lower step or the higher step. So if the little girl here tried to step halfway up the step, her foot would fall back to the step that she's already on. She can't step halfway. The work function is the amount of energy required to move an electron from an atom of a metal. If the amount of energy put into an electron is greater than the work function, it will be in the form of kinetic motion energy, and that will eject the electron from the atom at a high speed. So if you use the formula Ke equals 1/2 mv squared. So if you put in more kinetic energy and the mass, of course, stays the same, then there'll be a greater velocity. It will move faster. By the way, look at this term work function. What it is, it's the amount of energy required to remove an electron from an atom of a metal. The amount of energy required to remove electron from a gas is called ionization energy. So that's something you learned a long time ago. So work function and ionization energy are similar. So ionization energy applies to gases, removing an electron from a gas, and work function applies to metals. Okay. White light is made up of all the colors of light mixed together. By contrast, if you mix all the colors of paint together, you get black paint. So it's interesting that they're complete opposites. When white light is passed through a prism, it is separated into each of the component colors of light. This produces a continuous spectrum, like the one shown in figure XX. So over here is a continuous spectrum. I know it's not very good in black and white. I'm actually going to give you some of these things in color tomorrow. But this down here, there's an acronym that you remember, a mnemonic. It's Roy G. Biv. But Roy G. Biv is spelled backwards. So Roy G. Biv is spelled backwards. Roy, R-O-Y, G, B-I-V. This is the lowest energy. This is red. It's the lowest energy. And down here, violet is the highest energy. But the colors are red, orange, yellow, green, blue, indigo, and violet. I kind of always thought indigo and violet were kind of the same thing, but apparently they're not on this scale. So these are the high energy. So that means they have high frequency, short wavelengths. These have lower frequency and longer wavelengths. And all of them move at the speed of light, 3 times 10 to the 8 meters per second. All right, so this produces a continuous spectrum like the one shown in figure XX. I think I meant to put a figure 4 there. And individual elements emit specific colors of light. This produces a line spectrum. Again, this doesn't appear very well here. I'll give you, but for example, for hydrogen, you end up with these 4 spectrum lines. Unfortunately, we can't afford at this school a device that can allow you to see those, but there's actually devices that will allow you to show that this is red, this is green, this is blue, and this is violet. And that's a very specific spectrum. Let me show you. I'm sorry, I'm off screen. That's a very specific spectrum. So this again is red, excuse me, red, green, blue, and violet. This spectrum is specific to hydrogen. It's like a fingerprint. And it's how they can tell what elements are in stars that are thousands of light years away, is by taking the light that comes out of those stars and breaking it down, and they know that hydrogen has a certain pattern, helium has a certain pattern, lithium, beryllium, they all have their own unique line spectrum. So when you have individual elements, you have these individual lines, and as I say again, I'll give you a copy of one of these so you can see it, whereas a continuous spectrum is what you get from the sun. It's just white light broken into all the different colors, and that's what you would get out of the sun. So this produces a line spectrum, such as the one in figure 4. It's actually figure 5. Each element produces a unique spectrum of light, and it is by analyzing light from distant stars that astronomers can determine what elements make up the star. The line spectrum of hydrogen has 4 lines, blue, violet, blue, green, and red. Okay, how is light and color made? And this is an interesting topic. Where does color come from? When an electron falls from a higher energy orbital to a lower energy orbital, it gives off an electromagnetic wave. If the wavelength of the wave is between 400 and 700 nanometers, it could be a little less than 400, a little more than 700 actually, then the wave is visible light. Johann Balmer discovered the line spectrum for hydrogen shown in figure 6. The Balmer series is important because it emits wavelengths that produce visible light from an electron falling from the second orbital, falling to the second orbital from the 6th, 5th, 4th, and 3rd orbitals. In other words, of all the electromagnetic waves, it's only the Balmer series that produces electromagnetic waves that we can actually see, that actually stimulate the nerves in the back of our eye, the cones and the rods, to produce the sensation of light and of color. That's called the Balmer series. Okay, an equation for each of these wavelengths was developed by Johannes Rydberg to determine the wavelength of light that will be produced for the hydrogen spectrum. So the thing about these equations is it only applies to hydrogen. You say, well, what good is it? Because it at least gives a theoretical basis, and for hydrogen, at least a practical basis of how to know what color light it's going to get. It's kind of a scary-looking equation, but it's really not that hard. An equation for each of these Rydberg to determine the wavelength of light that will be produced for the hydrogen spectrum. Let's look over here at this real quick. There are three series. The Paschen series, which is falling to the third orbital from the sixth, fifth, fourth, from the seventh, sixth, fifth, and fourth. So if an electron falls to the third orbital from any of those higher orbitals, it'll form what's called the Paschen series. Those are electromagnetic waves, but you can't see them. They're not of a wavelength and frequency that stimulates the cones and rods in your eye. So while they are electromagnetic waves, they do not stimulate your eye. The one that does is the Balmer series, and that's falling to the second orbital of hydrogen from the sixth, fifth, fourth, and third orbitals. And that's what produces visible light. Another series that goes from the fifth, fourth, third, and second down to the first orbital is called the Lyman series. Again, that doesn't produce visible light. By the way, the Balmer series is a lower energy light, lower energy than visible light. So that would be what's called an infrared wave, and that's what heat produces. Whereas the ones that fall the furthest produce more energy. That would be a higher energy wavelength of light, so those would be above the visible light, and those are called ultraviolet because they're above violet on the visible light spectrum, so ultraviolet, and this would be ultraviolet, would be the Lyman series. All right, so this equation, it looks awful, but it's not that bad if you practice it. You got to get used to working in scientific notation for this part of the course. So it's saying that 1 over the wavelength of light is equal to the Rydberg constant, and there it is right there. It's just a scientific notation, a constant in scientific notation, equals 1 over n1 squared minus 1 over n2 squared, where n2 is the higher energy level and n1 is the lower energy level. So let's just say we were trying to find the wavelength. And notice, by the way, be careful on this. It's not the wavelength, it's the reciprocal of the wavelength. So when you get your final answer, you're going to have to flip it on your calculator. You're going to have to get the inverse. But if we want to get the wavelength here, what you do is, let's say we're talking about the Balmer series. If it falls from the fifth orbital down to the second, that would be a wavelength of visible light. Then the lower orbital is n1, so it would be 1 over the second orbital, or 1 over 2 squared, that's 1/4. And this would be 1 over 5 squared, because it fell from the higher orbital as the fifth orbital. 1 over 5 squared is 1/25. So it's 1/4 minus 1/25. You just do that on your calculator. You multiply it by this number. You'll get a number, and then that'll give you 1 over the wavelength. You take the reciprocal of that, and that will tell you the wavelength of that particular color of light. So it's how you can figure out how much light or what color the light is based on what orbital it fell from and that it fell from. So let's take an example here. And this will wrap up our lesson for today. What wavelength of light is produced when an electron falls from the fifth orbital of hydrogen to the second? So that's the example I just gave you. So here you go. So N2 is 5. That's the one it's falling from. And N1 is 2. So, and there's the Rydberg constant. So it's the Rydberg constant times 1/4 minus 1/25. If you do that on your calculator, you get 0.25 minus 0.04. That'll give you 0.21. And then you multiply it by this number. Again, you're going to have to work in scientific notation. Get used to that. That'll give you 1 over the wavelength. And then if you flip it, you get this number right here, or 434 nanometers. Notice that's in between the 400 and 700 nanometers that we said visible light would be. And it's on the, well, anyway, that's what that would give you. And that would give you a blue light, okay? That's on the lower end of the wavelength. That means it's higher frequency, more energetic light, and blue is toward the high energy end of the wavelength. Okay, so that's going to wrap the lesson for Tuesday. Again, this is due on Friday, but we'll try to get to work tonight. So if you have questions, you can ask me in the next couple of days. And I'll put the solutions to the exercises on a different video. Have a good day. We'll see you in class tomorrow.